when they do this to indicate which force is acting on which object, and it does matter. Now, if the student did the box here and did that, and the ground and did that, yes, I have a pretty good idea of what the student's thinking. I can live with that. Sometimes there'll be overlap, and I'll see something like that, and I'm going, all right, I'm guessing this goes with the box and that goes with the ground, and so you might see me draw a line like that, just so that I can identify it more clearly. Rookie mistake number 2. The number of times I've seen this. Not giving yourself enough room to actually do the work. Also, I can't tell which one goes with which one, but give yourself room. Rookie mistake number 3. Put the mystery cup sticker there. All right. Backwards. All forces have a source and a receiver, and you're drawing the forces on what's receiving the force. You're not drawing it on what's creating the force. So this upward force is what the box exerts on the ground. The downward force is what the ground exerts on the box. I need to draw it like that. This is the force on the box. I need to draw the arrow on the box. One other side note, if you're looking at other sources, you probably won't see force diagram, but it's free body diagram. In the free body diagram, it looks the same, except for the fact that they reduce the body to a single point. And so this would be the box, and this would be the ground. I tend not to use the free body diagram because when you get into rotational motion, it is helpful to know exactly where the force is being applied, so I just think it's better to start at this point. But if you see free body diagram, it pretty much what we're doing right now, except I draw something to represent the actual object and not just something more obvious what it represents than just a dot, where I have to actually label it. Alan?
What is the amount of weight that the box is, or the amount of weights in the problem? Period.
I didn't give enough information to know that. If I told you the mass of the box, there's a formula for weight, W equals mg, the mass times the acceleration due to gravity, which near the surface of the Earth is roughly 9.8 meters per second
Okay, so
squared.
you just didn't go over that yet.
No.
Cool.
All right, we're ready. Box on ground. So first I'm going to draw what's going on. I got ground and I got a box on it. You never saw that coming. Now first thing I've drawn it. So the next thing is I need to draw the object, so I've got room for drawing. I am not claiming that the box is in the air. All I've done is I've drawn the box, I've drawn the ground, and I've given myself room. I got my checklist here. Now the ground hopefully looks like it's level. If it's not level, if it looks like I intended it to be level, then it's level. If you're not sure, ask. But I'm not going to play a game where I'm going, it was at a 1 degree angle. I can't believe you missed that. No, if I draw it like it looks like it's supposed to be level, it probably is. All right, can you get rid of anything?
Friction.
Why?
It's not moving.
No desirable.
Oh, not a question of whether it moves or not.
The desired
Desired
relative
relative
motion.
Yeah. The box is sitting on level ground. There's no reason for it to move anywhere.
Tension.
Why?
No pulling.
All right.
I think
Why?
there's something said.
No, just guys.
No other, because there's no other.
Just guys.
Nothing else was mentioned. Normal?
Yeah, for us, we keep it.
We need it because it's
All right.
perpendicular to the ground.
If there were no normal force, the box would still be in free fall. All right, so let's do gravitational force first. I always find that the simplest, but you might do it differently, but which way is the gravitational force or the weight acting on the box?
Downward.
And on the ground?
Upward.
All right, done. And the normal force?
Perpendicular.
What'd you say, Pratika?
I said perpendicular to the box.
One more time.
Perpendicular to the box.
Perpendicular to the surfaces of contact. The surface of contact is this way, so therefore it would be vertical. Which way is it acting on the box?
Upward.
Yeah. And on the ground?
Downward.
If you were standing in the soft ground, and then you stepped away and you looked back and you saw your footprints there, this is what's causing the footprints right there.
Wait, so in the problem, the box falls to the ground and it's not just on the ground.
In the first case, it was falling.
Yeah.
This case, it's actually on the ground.
Oh, right, so when is the second diagram for?
This is the drawing of the problem itself.
Yes.
This is where I'm actually doing the force diagram.
Oh. Why is the box in the air?
So you got this.
I've just drawn a box.
Alright,
Yeah, the box is not in the air here. The box, I've just drawn a box with room for me to work. I've drawn the ground with room for me to work. I
okay.
find it helpful to draw them in the same orientation, but I could have done the ground here and the box like that.
Yeah.
But I find it helpful when thinking through, well, weight points towards each other, so that orientation, I find.
But
Tika?
you're saying, oh, I'm sorry.
Sorry, Jillian, one of you.
I'm sorry, no, you called her first, I'll wait.
Do we have to mention that we left room and the box is actually touching the ground, or?
No, the problem is the box on the ground, so that's the problem itself.
Okay, that's what I was gonna ask, so like,
Okay.
cause that's the question I had too, like the box is not in the air right now, so that second part is just kinda like separating it so we can see it better?
Yes, and when you do the analysis, as we get further into this,
Mm.
in order to do analysis of the box, we need to figure out what are the forces acting on the box.
Okay,
And so that's why it's especially important to have the box here and drawing the arrows on the box separately. So now, if we went to that next step of what's the acceleration of the box, well, I know these are the two forces involved.
okay, so it's just like, it's just separate, so it's like she said, showing room.
Yes.
Okay, alright, but
Absolutely.
it is still on the ground like that?
Yes,
Just- Okay,
yes.
perfect, okay. Cause I thought it was like falling, but it was,
No,
it didn't make
no.
sense, okay, alright.
Other questions? All right, here we go. Box. On box. On ground. Yeah, I'm sure you've heard legends about this. So first thing I'm gonna do, in case you're not quite sure what a box on the ground is, I'm gonna draw the ground with a box on it and a box on top of that. I know.
Wow.
Yeah, that's the right reaction. Now, I'm gonna label this as box A and box B. If you don't like that, come up with your own nomenclature. All right, so the first thing I'm gonna do is I need to draw them separately so I got some room to work. And again, I recommend them in the same basic orientation as we have right there. Got the checklist. Is there anything we can get rid of?
Friction, because there's some desired motion.
Or friction,
Because there's some desired motion.
okay.
Tension?
What?
Let's see, because there's not a force pushing towards each other.
Friction's a pulling force.
Oh, it's not pulling towards each other. I mean, it's not pulling, there's not a pulling force.
Yeah, I don't have a rope or chain or anything like that pulling
Right.
on it directly.
Other,
What, why can't you get rid of other?
yeah, I would say there's like a force pushing or pulling on
So it's the same as last time, it just got normal and gravitational. Let's do weight first. Which way is weight acting on what?
Downward for A and B and upward for the ground
So downward on A
and B
and B.
and upward on the ground.
Like that?
Yeah.
Okay.
Well, but
No,
there would
we'll just be
also
once.
be, am I tripping? Would there also not be an upward force
Yeah, there would
of
be a,
B to A, cause it has its own, why is it doing
We got
For
gravitational force
gravitational
upward
gravity.
on B. Why?
Cause B has its own, I'm ignoring. I don't know where my brain is going with this.
'Cause wouldn't
I
AB
believe a place many other students have gone, but was there an argument for an upward force on B?
yeah,
Yeah, because wouldn't A be
It
resting
was,
on
but I
B?
think,
A is resting on B.
Would it be a normal force instead of gravitation?
There's a normal force between them, definitely.
is the reason it's not on B because A is already pushing on B, so there wouldn't be two forces at the same time on B?
No, you could have multiple forces acting on it. All right,
Okay.
so let's cut to some chase here.
Okay.
The generalized gravitational force just required two masses. There are two masses. There is technically a gravitational force between A and B. It is so incredibly tiny, we are ignoring it. The people who would care about the gravitational force between A and B are the people who do gravitation studies. One of the gravitation studies, I saw a lecture a while back, and they did in grad school, 20 years ago. They were getting different results in the spring and in the fall. And they couldn't quite figure it out at first. And then eventually they figured out, this is how sensitive those experiments are.
Pollen?
Pardon?
Was it pollen?
No, not pollen.
Is it because of the sun? Because like since like when you're summer, you're facing the sun more, so there's like. Actually, never mind.
No, it's actually the rain. More rain in the springtime than in the fall. That the physics lab was in the basement of this building, and on the other side of the brick wall was dirt. And in the spring, when it rained more water was soaked into the hill, and that threw off their experiments.
Silly.
We are not doing those. We don't have the multi-million-dollar equipment to notice that kind of stuff. So let's say that you go in, well, the force is still there, so I'm gonna put it down. Okay, let's talk about the path to madness. If you're gonna talk about the gravitational force between A and B, then why not the gravitational force between the top part of A and the bottom part of A? Or take it one step further. ... between the atom, one atom in A and the other atom in A, and then so forth. You could take it all the way down to the atomic level. Actually, you could take it down farther than that if you wanted. In which case, that'll be the first problem you start, and that's the problem that you're still working on when you die. Probably from lack of food, because that's all you're doing. So those tiny little forces we are not worried about when we do these force diagrams. We will somewhat take them into account in 152. There's one particular case, but still not the tiny forces. There's small, but not tiny. So
That is to say, you won't count off any points for you.
if you label it correctly, if you label this force between them as a weight, yes, I will count off of that because it is not a weight.
Yep. There's 1 trillion down arrows for y.
At some point, I'm gonna get tired, and who knows how I'll react at that point. All right, there is a mistake up on the board, though. Jillian, you had a question?
Before you go further, I meant to ask, why do you have 2 arrows from the ground up?
That's it. Hey, somebody answer that? Why are there 2 arrows up on the ground?
There's
Just
2
two
boxes.
Each force comes in with a pair, so this is paired with one of them, that's paired with the other.
Oh, okay, so one for A, one for B.
Yes.
Right, okay.
Which one's for which? Oh, Margaret?
like it's not necessary, it's the same,
Yeah, they're both.
why
it's
can't we
pretty
just
much-
draw one?
Because they're not the same.
They're not the same.
No.
You have them labeled the same.
Which is the problem. And one of the reasons I do box on box is the fact that I have two small objects, small relative to the earth, two small objects, I do need to differentiate between them. So, W sub A, one of these is W sub A, this is W sub B, W sub B. They are not the same. Now, I typically do a subscript related to the object itself. So in this case, box A has an A, box B has a B. Other people, they put in these in and they just start with 1, 2, and then just keep working their way through, or A, B, C, D, however many there happen to be. So we have the two small objects, both weights going down. So the biggest mistake I see at this point is people forgetting to put in the subscripts. I got away with no subscripts before because I had only one small object. Normal force.
On A,
Going which way?
upward.
And where's the other part of that pair?
Going downward on B.
Okay. Oh, that's a mistake. That should be A, twice of A. Because they're the same magnitude of force.
Would there be one at B and the ground too?
Yes. Acting which way on B?
Upward.
And down on the ground.
If we do that next to the box, is that fine?
Yeah.
Okay.
Would there also still be one with A in the ground? Or?
Normal force requires contact. A is not touching the ground. And Jedi powers are not part of this course.
Damn.
The metachlorines are weak in these objects. Now, all this is well and good, but what application does it apply? Is there any application to this? Well, there happens to be. So we're gonna do a slightly different problem, but really the same. Person standing on scale. Ground, that's my scale, and that's my person. So not box on ground, it's person on scale on ground. So I'm gonna draw the three objects. I got my ground, I got my scale, and got my person. Force diagram's gonna look the same. I'm gonna use different subscripts just because we're dealing with some different things here. So I've got weight of person, weight of person. I have weight of scale, weight of scale. I have normal force on person, and then person there, and then scale. Let's see, ground's moving the scale up, and the scale's pushing down on the ground.
Question,
Yes.
will you always specify that all of the stuff previously will be on the ground? If it is supposed to be on the ground?
If an object's on the problem would need to state that an object's on the ground.
Yes, so I'm just asking, like, you wouldn't do person standing on chair when you don't specify the ground, so they could just be doing that mid-air or something?
Properly, I should specify the chair's on the ground.
Yes.
Or I've got to give a drawing where I've drawn the ground.
Yeah.
So if I've done this, supposedly this is worth 1,000 words. Well, depends on the resolution, but anyway. All right, so here's the question. Now, first off, are there any questions? I'm hoping that you can see that this is very similar to what we just had. The only difference is the subscripts and the shape of the objects. All right. When I stand on the scale, what does it measure?
Your weight.
No, no.
Is that your,
Weight is a gravitational force, so it is not measuring the gravitational force, it's not measuring my weight.
is it your mass?
Pardon?
Your mass.
No. Balances measure mass, scales measure force. Mass is not a force, mass and weight are not the same thing.
The gravitational force that the Earth is, okay, alright.
Measuring your normal force?
Yes. If you look at this, what is the only force that the person is exerting on the scale? That is the only force the person exerts on the scale. When I step on the bathroom scale, it is measuring the normal force I exert on it. Gravitational force acting on me is between me and the ground. So this is what is actually being measured. So if I stand on an analog scale and bounce up and down, my weight is not shooting up to 400 pounds and then down to 50 pounds. My weight is not changing just because I'm bouncing on the scale. What is changing is the normal force.
So when you said the gravitational pull, oh, so the gravitational pull you said is between you and the ground?
Yes.
Not the scale.
Correct.
So the normal force is between you and the scale?
Yes.
Okay. Okay.
Because this force right here, the weight of the scale is from the ground. This normal force on the scale acting up is from the ground. This is the only force that I exert on the scale.
Okay.
Other than an incredibly tiny gravitational force, not a weight, but there's a tiny, like 10 to the negative 10th newtons kind of thing.
Okay. So the gravitational pull, is there, let me see, I'm sorry, I can't see. So is there a gravitational pull between the scale and the floor?
The scale on the ground,
Yeah.
that's this WS.
Oh, okay. Okay.
So like if there was a scale right below that scale, scale number 2 would be using to find the force of scale number 1.
Yes.
Okay.
So, just again, why doesn't the, like, the yellow arrow down, weight of the person matter on the scale?
Because the gravitational pull, the weight,
Is between there,
yes, it's with the earth. The
but,
scale just happened to be in between.
okay.
So